Alrighty everyone, welcome back. Just cleaning up the board here. Today, if you've forgotten, is double lecture Friday, right? Because your exam is next week. Recall that we're having double lecture today because I think you would prefer to have the review on Wednesday, the Wednesday before the exam, much rather than today, right? Because if I had it today, then there would be 2 lectures between now, your review, and the exam, plus you have an entire week from the review to the exam. You may not remember everything. So, to avoid that, and I don't think anyone wants that, no one ever has, we'll have the review on Wednesday before the exam. Makes sense. However, that's what we need to use that extra hour for. I mean, that's why we have this extra hour. But the extra hour is today, not Wednesday. So as I explained before, sorry, double lecture. Now, maybe this is the one time that the COVID thing has been good to us, because, you know, if you get a little burned out on 2 lectures back to back, which is fair, then just watch the next one on Saturday, right? But don't watch all of the class in, what are we at, 15 hours, something like 15 hours we've had of class now. I don't think it's a good idea to watch all of those right before the exam. That's not going to work. Now, with that said, I think that's obvious. After the exam, I will look at your grades and I will contact any of you who are doing badly. And just heads up, in the history of this class, generally 10-point spreads, 90 to 100 is an A, 80 to a 90 is a B. We've had 10-point spreads. Usually there's a curve, but a curve just for like if you're within 1% of getting an A, right? If you're 89.5, I'll give you an A, right? But other than that, if you have a 60 and you're thinking, oh, well, with a curve that's a B, actually that's an F, all right? So well, a D. Anyway, you're failing. And don't count on a curve to do something that massive. There's no way that's going to happen. I mean, it could, but there's no way that's going to happen. So if that does happen to you, I will make sure you know it because you'll hear it from me. So don't jump if you get an email, but this is something we have to do to make sure that you pass, right? Because you're supposed to be graduating. Anyway. All right, so double lecture Friday. Let's go ahead and review what we're doing. And on Monday, we introduced the concept of particles as waves, the de Broglie relationship. We developed the kinetic energy operator from the Schrodinger equation, and here's the Schrodinger equation in the form of an eigenvalue equation. So we talked about kinetic energy, which ended up being some constants to make the units work, a double derivative with respect to space and not time, which is weird, but okay, then it's a differential equation, so you're going to operate on a function. The function is the answer to the problem. Remember that fancy word scalar. It's multiplied by a scalar, but it boomerangs back, right? I'm using a lot of silly words, but it's just the best I can describe them, and the more I use them, the more you get used to me, then we'll do well together, right? Okay, so we introduced the kinetic energy operator on Monday, right? Wednesday, we talked about wave functions, how the absolute value of a wave function is a probability distribution, just like Maxwell-Boltzmann. Just like Maxwell-Boltzmann, you use it the same way to calculate averages. You would multiply the thing you want the average of times the probability distribution and integrate it. So quantum mechanics has lots of integrals. That's actually why we do quantum mechanics second and thermo first, because thermo is easier. There's a lot of derivatives. And derivatives are easier, aren't they? Integrals are like anti-derivatives, and they're harder. So we do that, and that's what quantum mechanics is, and that's why we do that second. Anyway. So we also talked about rules of wave functions, and this is a little silly, especially for the reasons I'm going to cover today. But 2 of them that are kind of important are smooth and continuous. So you can't have the wave function fly off to infinity. That's due to the probabilistic nature of wave functions. Remember the Born interpretation, B-O-R-N, Max Born, the Born interpretation is that wave function squared the absolute value of a wave function. Wave function times its complex conjugate, those are all the wave functions squared. those are probability distributions, and probability can't fly off to infinity. That doesn't make sense. It also has to be so that's smooth. It has to be continuous. Here we see a wave function that's saying that the particle has two probabilities to be in one spot. That doesn't make any sense. So no, that doesn't work. The other criterion we talked about was that the energy has to make sense. There's only certain allowed energies. It depends on the type of problem you're working on, the type of model. So as we build our quantum fundamentals, what we do pretty soon, week after next, is we're going to start looking at model problem after model problem, which start out kind of silly, and we're going to talk about that today. And then we talk about bonds, chemical bonds, and then we talk about atoms, and we talk about the hydrogen atom wave functions, and then actually we're at the end of the class. So this is I use the example, I've been bringing this up constantly at this point, the particle in a box. So it's a particle in a trap where to be left of 0 or right of position L means that you have infinite potential energy, which a particle can't do, which is just to say that the walls are made of steel. Okay, let's just say that. And I can associate a wave function with an energy. All of this works together. And only certain energies are going to have like nodes at 0 and L, which is necessary. Otherwise, the particle leaks out of the box. Leaks to the left or right of where the walls are. Okay, only certain energies have the wave functions set to 0, have nodes at position 0 and L. Okay, now let me draw what that means. That'll make it a little bit more clear. Now, this wave has a certain energy, and I know that by doing this, the Eigenvalue Equation. I know enough about this, and you'll be able to do this too by the end of the class. I know instinctually what a lower energy wave would look like. It's less curvy. That's a hint. Okay, let me draw you a less curvy wave, and I'll dash it so that you don't get confused what's what. Okay, so this is ostensibly a lower energy wave, but what's wrong with that is that it clearly leaks left and right of the walls of the box, which it can't do. This actually isn't a low energy wave, it's technically an infinitely high energy wave because that's what it would need to get outside the box, so that doesn't work. As I scan more energy, as I scan up in energy, I find this one, and then as I go higher, I have this problem, but then I find another energy that's okay, that has nodes at point x equals 0 and point x equals L, which is this one. And then I can keep going, and I'll find even another wave, which will have more nodes, and it's wavier and higher energy, and on and on and on. And again, we're going to do this problem shortly. Alrighty, and remember I also mentioned that this is the quantum and quantum mechanics. This is like 1 unit of energy, and this I think is like 4 units of energy, and guess what? The next one would have 9 units of energy. So if I could do spectroscopy on this, I would see peaks corresponding to the absorption of energy from a particle in this state to a particle in that state. I would see that transition as a spectroscopic observable. So this is what quantum mechanics is good for. All right, so what? Okay, so we're not ready for the particle in the box yet, so I don't know why I keep talking about it. What I want to do is spend a little bit more time on wave functions and tell you that for today, the extra lecture, right after, is we're always working on example problems, paradigms, and in what we're starting out with is the V equals 0, right? Notice I didn't write potential energy in the Schrodinger equation, and when I set the potential to 0, and we're only going to work in X, let's forget Y and Z, that is called the Freeway problem. Okay, a free wave. And we're going to do build up our mathematical abilities on the free wave with no potential energy problem. Okay, so in hint, the answer is sine and cosine. So whatever. But I hate to bring this up, but here's the thing. I am compelled to be honest about this, but there is a slight problem with the Freeway. The Freeway, again, is a great way to start learning quantum mechanics, and I'm going to do that because you really need that. But there's a slight problem with the model, and let me give you a hint what the problem is. A particle in one dimension and there's no potential energy. Now what that means is that the universe doesn't end. The universe doesn't end to the left or to the right. There's no potential energy. That means that there's no walls, like ever. That is highly unrealistic, right? So this is a particle in a one-dimensional universe by itself that never ends. That is not realistic. And because of that, there's a flaw with this model, and I'm going to explain that. Now, to explain what's wrong with the model, let me point out that, and don't write this down. Don't write this down, but remember that wave functions give us energies, but by themselves, they're probability distributions. And we've covered probability distributions like Boltzmann, right? Here's the business end, the top part. And on the bottom, of course, is a normalizer where we make this summation. And whenever you had a Boltzmann or Maxwell-Boltzmann problem on the exam, which is really freaking soon, just like that homework example, the way you approach this is you have to figure out what the normalizer is. There's an identity for the sum, or you turn the sum into an integral, and then it's easy from there. Integrate it, it's 1. Integrate it times energy, now you have the average energy. Anyway, we've done all this. Okay, now the question is, that's the Boltzmann distribution. Now let's look at a wave function squared. And a free wave, like cosine, let's just say it's a cosine, it is a cosine. All right, let's take cosine, kx. We're used to kx. Okay, let's square it. Where's the normalizer? It has to have a normalizer. But where is it? So here's the problem with quantum. I said this last time. The damn thing is different than Boltzmann. Boltzmann comes with a normalizer. It'll always work, so long as you don't mess up the algebra. It's going to work out just fine. Everything works out just fine. Quantum, we can often solve wave functions, but it doesn't have a normalization that automatically comes with it. Take for example, this guy right here. Look at this. I know what this wave function is. Here, let me do this. What is that wave function? I can figure it out. At x equals 0, I better have the wave function equal to 0. Okay, well sine does that just fine. So I put it in x. When x goes to L, this is a half wave, so I better travel pi. So look at that. See, I figured out the wave function. Sine pi x over L. When x goes from 0 to L, sine goes from 0 to pi, which is a half wave, and that's one of the right wave functions. Fine, but is it normalized? If I square this and integrate it from 0 to L, do I get 1? Hint, the answer is no. You do not get the number 1. I was able to figure out the wave function from pure horse sense. I didn't have to use a Schrödinger equation. I just know what it is. It's a wave, and sine and cosine are wave. And then I just made the innards work. In fact, try this. Try plugging it into here. What's the double derivative of sine? It's minus sine. So I get the minus sign. I get, sine and sine. I pick up a minus sign, but there's a minus sign here. So what I end up with is an energy of h bar squared k squared over 2m, which we all know from our from Monday's lecture, actually, right? That's energy. Okay, so I figured this out, but it's not necessarily normalized. You often have to normalize it yourself. Now, the way you do that is, of course, you are going to take the wave function squared, you're going to integrate it over all limits, and let's just, again, it's just x, and it's going to be 1. Now, in this previous example, the way to do this is I would multiply it by a constant n, which is the normalization constant, and then figure out what n is to make this work. Okay, now, the way that this will turn out every time is, let me write down the normalization here. I know I'm kind of like all over the board, but sorry. All right, the wave function, which I just used my horse sense to figure out, which you would be shocked how often that's how you solve even really complex problems, by the way. Regardless, I am going to take the thing I figure out, square it, so that's cosine. I squared it, and then I integrate it over all limits. Let's say that's minus infinity to infinity. Okay, but technically, yeah, that's actually it. That's actually it. So that's the normalization. Now, what that means is that the wave function itself, a normalized wave function, is this. I'll call it norm so that you realize it's normalized. It is the unnormalized wave function divided by the integral. And again, I don't know what the limits are. Like in this problem, the limits would be 0 to L. So I'm just going to put minus infinity to infinity without knowing any better. So then that's the wave function squared. And again, just partial of x, I'm just assuming we're one-dimensional. However, there's a square root. Right. The square root comes about because the wave function squared is the probability distribution, not the wave function itself. Okay, so this is the proper form for a normalized wave function. And again, the point of all this is that you often have to make sure yourself that it's normalized because of all the reasons I just said, that you often figure out wave functions on your own. It is prudent to assume that wave functions are not normalized when we're working with them. You should always, if it matters, if the problem is, let's think practically. The problem is you're at your exam and the question is the wave function normalized? Check. Check to see, does it look like this? Or if you integrate it from the limits, do you get 1, right? So you should always check whether wave functions are normalized. All right, now with that said, let me tell you the problem of the free wave. Now again, the free wave is no potential energy and x goes on forever. All right, now I can tell you, I'll write this down, free wave, that a valid wave function is cosine kx. Okay, and there's a couple more, and I will actually write those down shortly. Okay, and if we do that, if we do a little bit more work, we know that actually is, remember that we solved what k is. 2m energy, 1/2 over h bar. Okay, so there we go. Again, don't assume it's normalized, right? And hint, it's not. Okay, so let's normalize it. And this is the problem. Let me just stick with cosine kx because I don't want to write all that down again. Okay, now again, we take the square root of the integral over all limits, and the limits, I need to tell you what the limits are. In the particle in the box, I tell you the limits are 0 to L. In the free wave, the limits are minus infinity to infinity. I'll tell you that because look, you kind of should be able to figure it out, whatever, I'll tell you what the limits are. Okay, so integral from minus infinity to infinity, cosine kx squared dx. Who knows what that integral is? Well, I'll tell you what, let's graph it. Let's graph it. Cosine kx, doesn't matter what k is. Let's graph cosine squared starting at 0. Okay, 0, 0. Now being squared, it never goes below 0, right? It's just a wave that goes on, and it's always above 0. The integral is the area. And don't forget, this thing goes on forever to the right and to the left. This is infinity. The normalized wave function is cosine kx over the square root of infinity, which is still infinity. That is the problem with the free wave. All right, so I spent a lot of time on this. Most people try to cover this up, right? Most classes in textbooks try to cover up this problem, but it bothers me. I want to tell you that, again, this model problem of the free wave has a problem where the normalization is technically infinity, 1 over infinity. That violates the concept of the wave function not being 0 everywhere. Remember when I talked about that last lecture on Wednesday? I said the wave function can't be 0 everywhere. This violates that. Again, the reason is due to a flaw in the model itself. The universe is not infinite, so Stephen Hawking says. There's other things in the universe that basically are walls. This is a particle by itself, and there's no walls, and it goes on forever. That's not realistic, nor is the answer. However, this wave function, we're going to ignore the normalization constant because you kind of have to. This is a very good substrate to practice on. This is going to be our quantum mechanical practice, but it does have this flaw. So anyway, I just wanted to point that out. And I have accomplished one other goal is I've gone over normalization to kind of an extreme. Okay, so now what? Let's see here. I told you about particle in the box. How am I doing on time? I'm doing really good on time. Okay, so I think I have beaten this to death. But tell you what, I actually do have a lot of time. Why don't we look back at this particle in the box, and just so it's super clear, I actually don't have notes on this. I'm now speaking off the top of my head. Let's normalize this. This is not normalized, right? So let's normalize this. Sorry, everyone, a problem with the camera. All right, so like I say, just to make sure that you get this, let's figure out how to normalize that ground state wave function for the particle in the box. All right, now what it means to be normalized is that the integral of the wave function squared, the n squared sine pi x over L squared, don't forget your partials, over the proper limits, and I'll always tell you what the proper limits are, has better be equal to 1. Okay, now, how to go about this? N squared is a constant, so let's take it out of the integral. And now what I can do is I can solve, remember that's a therefore, n squared is, since all this is equal to 1 over the, oh, that line is slanty, I don't like that. There we go. 1 over the integral from 0 to L of sine pi x over L dx. Okay. Which means n itself is, just take the square root. Square root of 1 is 1, so there you go. All right, with that, then you know that the normalized wave function, and tell you what, why don't you try it on your own? Actually, it's probably been one of your homeworks or an exam, so you're going to have to do it no matter what, so you might as well do it now. Figure out what n is, and I'll tell you what it is. It ends up being square root of 2 over L. So here's the normalized wave function. Okay. And if you're not sure, take this and square it, integrate from 0 to L, and do that online. Use that online integrator that I think I've had you use it a few times now. And sure enough, you find that interval will be 1. So that's your normalization constant. All right. So with that, I have hopefully beaten normalization to death. I've told you quite a bit about the free wave, and we have a lot of things we're going to do with the free wave. And you may be thinking, like, well, what else can we do with it? All right. What I've done is I've tried to introduce the Schrodinger equation, and we've talked about kinetic energy, and it operates on the wave function, and it gives the energy, and then the wave function has to boomerang back. But it turns out that what I have given you is a very specific example. Quantum mechanics is more than the Schrodinger equation. Tell you what, give me a moment to wipe out the board, and I'm going to show you just how expansive quantum mechanics actually is. All right, so now I have to admit my head's kind of jumbled up here. This is when I'm going to start, unfortunately, kind of complicating things a little bit. Let's remind ourselves, what have we seen? We have seen the Schrodinger equation. Let me use some shorthand. Oh, and a new pen. We have seen it this way. The eigenvalue equation. And this is the Hamiltonian. And in our free wave problem, that is simply kinetic energy, h bar squared over 2m. Double derivative minus sign because double derivatives return minus signs. Right, so that's kinetic energy. That's the operator, that's the kinetic energy operator. The absence of potential energy, that's the Hamiltonian, which goes into the eigenvalue equation. Yeah, I know that's a lot of words, but it's not that bad, right? Okay, so it turns out that there are other operators. Let me give you one example. This is one dimension. Right, so 1D. There's a 3D form, which would be minus h bar squared over 2m. That's always there. If you wanted to add more dimensions, which we'll do in about 2 weeks, you simply add in double derivatives of x, y, and z. Okay, now the point of this is to reveal there's more operators. Right? One-dimensional kinetic energy, three-dimensional kinetic energy. Guess what? I can kind of keep going and going and going. So the Hamiltonian, I already wrote that down. I don't know why I'm writing it down again. This is just one operator. It's one operator out of many. Because it gives, this one's important because it gives energy. And that's how Schrodinger originally designed all of this. So again, the Hamiltonian operator is an important one because it gives energy. We think of the wave functions of the Hamiltonian, the things we've been working with, the cosine kx. We think that those are special. We think that those are real. They're probability distributions. In your freshman and maybe high school chemistry class, you've seen orbitals of 1s, 2s, 2p orbitals, right? You've seen them before in this class. Those are wave functions for the Hamiltonian that corresponds to like the Hamiltonian for a hydrogen atom. Those are the wave functions. You've been told that those are real, right? This is really how this works. It turns out there's other operators that give something other than energy. They can give position. There's a position operator, cleverly called the position operator. It tells you where things are at. There's a momentum operator. There's an angular momentum operator. There's a momentum operator that operates in only certain dimensions, like x, y, and z. I could express that for rotational angular momentum, and they could work with theta or phi. There's a operator for flux, right? Remember flux from Maxwell-Boltzmann? there are operators, there's a bunch of operators, right? Now, there's like 20 that I know off the top of my head. We're going to cover like 4 or 5 in this class. But anyway, so that's the important thing. So my generic operator, this is how it's traditionally done. I just give it a little omega, and remember, operators have a hat. Okay, so hopefully that's not too mind-blowing, and let me give you a little insight here. The position operator, it's just x. If position operator y, it's just y. Okay, so other operators, they're not too hard to understand. In fact, they're often easier than the kinetic energy operator. The kinetic energy operator is actually one of the hardest ones. Okay, so I have all kinds of operators. Now let me throw the difficulty at you. I'm going to not write psi for its wave function. I'm going to write this thing. And now we use the eigenvalue equation. Now notice I've written the Schrodinger equation with the Hamiltonian operator. It's still the same thing. I've used different letters, but that means something. Told you, a lot of this stuff at the beginning is just interpretation. This is for an operator that's not the Hamiltonian. If it was the Hamiltonian, I would have written an H. It's just a convention. It doesn't really mean anything. This is its wave function. I am simply using a different symbol for this, given that I'm using a different operator than the Hamiltonian. I'm not using E for the eigenvalue. I'm using a different letter because this operator doesn't give energy. It gives something else. It gives position. It gives angular momentum. It gives rotational energy. Again, there's operators for everything. There's an operator for flux. So this is the flux, right? And again, the wave function of the eigenfunction. I should use the word eigenfunction. Boomerangs back. So we often use the word wave function for the Hamiltonian operator, and I often try to use eigenfunction for any other operator. All right, now the reason that this is a little complicated is that, get this, wave functions for the Hamiltonian may or may not be the eigenfunctions of other operators. So, think about our particle in the box, our sine wave, our sine pi x over L. It works in the Schrodinger equation, the eigenvalue equation with the Hamiltonian, because double derivative of sine is going to give me the energy times sine. So that's a pass. It works. It satisfies the eigenvalue equation. Now let's take sine kx over L and ask the momentum. And I'll write down the momentum operator in a moment. Let me go ahead and tell you, it fails. It will not take the right eigenvalue equation form. I can tell you what's going to happen. I'm going to operate on the momentum times sine, and I'm going to get an eigenvalue, but I'm going to get a cosine. It doesn't boomerang back. That's a fail. What it means is that you don't actually know the momentum. Okay, now I'm going to, in case that's already been like, whoa, what? I will make that clear with an example. I'm just trying to give a big picture. Let me give a big picture in a different way. Operators have their wave functions, or eigenfunctions. The Hamiltonian has wave functions that are its solutions. By solution, that means it satisfies the eigenvalue equation. It looks like this, where that's a number, right, in joules. Other operators have their own eigenfunctions, right? I'm doing a little Venn diagram. These guys are okay with this other operator, again, which could be momentum or angular energy or blah, blah, blah. This guy will keep this thing happy because it works in the eigenvalue equation. The problem is that they may or may not be the same function. So this will always work with, momentum, but it may or may not work with kinetic energy. The sine function definitely works with kinetic energy, but it may or may not work with momentum. You have to try it and see. So once you figure out what the wave functions are, and I would figure out the wave function for the Hamiltonian, so it works for that. It automatically works for that. And then I have to see whether I can figure out the momentum or whatever else I'm being asked, whatever else I'm looking for. I apply that operator, and if I see the eigenvalue equation work, it's cool. If it doesn't work, it's a fail. And then I have to figure out something else. Okay, so we're going to spend a lot of time, this is what we're going to do in the next hour, is to understand that with some examples. So I have a few moments left. So let me write down some other operators so that you can see that, again, I told you there's other operators, but it's not real until I write them down. Okay, I've already told you about momentum. So what other kinds of operators are there? Well, there's the momentum operator. Now, this, hopefully you can kind of figure it out, because you know what momentum squared is. It's this thing. So guess what momentum is? Well, that's momentum squared over 2m. So momentum is h bar over I, single derivative. So there you go. So now that's the momentum operator. And you may notice that momentum squared is then minus h bar squared double derivative. Then you divide by 2m, and that's kinetic energy. So this makes sense. Okay, what else we got? Position operator. Now this one's funny. Just x. All right, so that one's easy. You probably could guess that. Okay, angular momentum. That's called J. We're going to be on that in about 1 month. And if it's angular, it still has that h bar over I, so it's still momentum. But being angular, I better not be seeing x, y, and z. I better see r, theta, and phi, right? So it has spherical coordinates. Okay, and then there's flux. And I think I have to give it a hat, right? Flux is this. These can look all kinds of different ways. You take the wave function complex conjugate, and we've covered complex conjugate, derivative, minus the wave function, minus the wave function, not complex conjugate, derivative of the complex conjugate. I don't draw stars very well. I have some like weird mental block because I was dropped on my head a bunch of times, but anyway, I don't want that to look good. Okay, so this is a flux operator. Remember we covered flux when we did Maxwell-Boltzmann. So this tells you how things are moving through like a surface, right? So remember we covered flux, that was the last thing we did in Maxwell-Boltzmann. Okay, so there's all kinds of operators. All right. Now, I want to do, the last thing I'll do, and we'll end a little early if that's okay because we have a whole other hour, is I mentioned to you that these may or may not work together. This is one of the damning things about quantum mechanics, and this is something I hate. All right, let's look back at our particle in a box deal. And here's the ground state, right? And we've already figured out that the wave function is normalized, and given that it goes from 0 to L. Okay. Now, this is designed to work with the Hamiltonian operator. So I know that it's going to satisfy the eigenvalue equation. Let's double check it. All right? Let's do that. There's h bar squared over 2m. Sorry, I'm speaking off the cuff. Sorry, my handwriting isn't so good. Okay. The normalization constant actually doesn't do anything. You may notice that it's just going to sit around. If that's not obvious, it will be in a second. Okay, so what do you get? Okay, let's see. Double derivative of sine is going to be minus sine. So, hold on. So let me put h bar. I should stick with the constants. Okay, double derivative of sine is minus sine, so I'll get rid of the minus sign. Okay, then it's going to spill out the innards twice, so that's going to be pi squared over L squared. Okay, and then the normalization constant, and then the wave function. Now, this, of course, is the eigenvalue, and so that's the energy. That is the energy of that state. Okay, so awesome. Wave function, operator. Why am I going backward? It's kinetic energy operator. Kinetic energy operator, eigenvalue, wave function. Okay, totally worked. All right, so this is exactly how you do quantum mechanics. Problem. I've given you this, you've shown me that you can get the energy, but now I've asked for the momentum. All right, momentum operator, wave function. What is that? I've written it down, h bar over I, derivative. Let's write the wave function. I've painted myself in a corner, that's okay. Okay, what's that equal to? Write down the constants. Sine, there's no minus sign. Single derivative is going to bring out pi over L. And then I've got 2 over L cosine. Okay. Is that the wave function? No. This is a fail. Fail. All right, so you can imagine I write this on an exam. Maybe I'll do exactly this. And I'm going to ask you, is this the eigenfunction? Is this the momentum? The answer is no. It's no because that's not the wave function. Operator wave function, eigenvalue wave function, but that's not the wave function. It's a fail. And that means that is not the momentum. That's not the expectation value. That's not the eigenvalue for momentum. If this was the eigenvalue for momentum, if this was the real momentum, then I would have had sine pi x over L. But I don't. So not only does this not work, that's not the right momentum. Now there's another hint to this. This is a hint. All right, number one is that this is not the wave function. This is not an eigenvalue equation. It's a fail. But here's another hint. Momentum is real. Momentum is absolutely something that is measurable. It is a real thing. If you want to call this the eigenvalue, it has an I in it, which is imaginary. Remember I told you, you cannot have eigenvalues, especially of things that are measurable, that therefore are real. Real things cannot have I in them. They can't be imaginary. Real things are not imaginary. That's what you tell the crazy people and you guys. But it does make sense, right? So, with that said, now what? Okay, I'm on time. All right, I'm almost out of time. We'll end a little early. We're going to resolve this problem. So, there's two things we can do about this. Number one is we can say we're allowed to know the energy, but not the momentum. That's kind of defeatist, but you will find that there are times that there are questions, and questions are basically operators. You know, I want to know the momentum, that's a question. The way to mathematically answer the question is to apply an operator. It is true that there are sometimes some questions cannot be answered. This is not one of them. I can tell you that the momentum of this is actually 0. I actually know the answer. The way to go about it is to be clever. This is actually answerable, just not this way. We're going to have to do some trickery, some mathematical trickery. Hint, the mathematical trickery is we're going to convert sine into e to the ikx minus e to the minus ikx. Right? Remember that imaginary stuff? That's what we're going to convert sine into in the next hour. And I'm going to show you how to use that, apply the momentum operator, and show that the momentum is 0. Now, here's the last hint. I don't know if I'm over time or not. But when you think about it, the potential energy, right, is infinity outside the box. Remember, this thing is trapped. Okay, how could the momentum be anything other than 0? If the momentum was anything other than 0, the particle would escape the box at some point. If the momentum is positive, even if it's small, it means at some point it gets out of the box. If it's negative and small, okay, it may take a while, but then it moves out to the left. If the momentum is 0, it's trapped. It never can escape. Of course it can't escape. It's in an infinite potential box. Okay, so with that, take a break, even a day-long break if you feel like you're a little overwhelmed. And next time we're going to solve this problem.